This is Brian Putt. Today I'd like to talk to you about doing Bayesian evaluations using simulation. Typically, Bayesian evaluations are done using decision trees. However, in some cases, models can get too large, too many uncertainties to make the decision tree practical. So we're going to look at simulation. Typically, Bayesian evaluations are involved in a value of information exercise. And those evaluations use decision trees. Today I'm going to go through an example using only simulation. We're going to start with a nearly blank worksheet and use SIPmath to develop the analysis. SIPmath is a free Excel tool available from probabilitymanagement.org. During the demonstration, I will demonstrate how you can get the correct probabilities for the Bayesian evaluation. If you just use typical simulation, you'll never get it right, even with 10,000 simulations. Sometimes the probabilities are quite small. Think about the COVID test reliability. This method will give you the exact numbers for those probabilities and match what you have in the decision tree, yet allow you to have continuous uncertainties in your model. Let's look at the Excel model. Okay, here's my starter Excel model. And what I've shown is that we have a test that's looking at whether, let's say, someone's infected with COVID or not. So they're either infected or they're not infected. And when I run the test, if they are infected, there's an 80% chance I'll know it, I'll recognize that, and there's a 20% chance that I'll give a false negative. If they're not infected, I will recognize that 90% of the time, and 10% of the time I'll have a false positive. So now how do I incorporate this into a simulation? Let's calculate the joint probability matrix. Oh, we need one more thing, which is the probability of reality. Let's assume that's 10% and 90%. Now I can calculate the joint probabilities. So it's equal to this number times this number. And I will simply hold the B constant and copy that across. And if I've done that right, the sum of these things should be 100%, which it is. You can see it down here. So now, how to incorporate these into a simulation? Well, if I'm using SIPmath, the first thing I have to do is initialize. So I'm going to initialize that. And I'm going to use 1,000 trials. And then what I'm going to do is set up a vector which represents the 1,000 possible outcomes of 1 to 1,000. I'm going to take this column and copy it. Get a new worksheet here for convenience. Paste it in here. I'm going to put a ran command here. Put a ran command here. Copy that down. And then I'm going to take these two columns and sort them. I now have a vector here that is random. I'm going to use this over my simulation to make sure I get the right number of counts for each one of the possible outcomes of the conditional matrix. What is the probability of each of the outcomes? This is equal to 0.08 and 0.09. And the occurrences are equal to the probability times the number of trials. And in SIPmath, there's a variable called PM trials. So we'll use that variable. And then we want the cum occurrences. And we're going to start here with 1 minus epsilon. I'll just put E, 1 point E to the minus 5, just for kicks. And let's get rid of some of those decimals because this is really going to be a whole number here. and this is equal to that number plus this number. So what's the reality here in this particular case? Well, I'm going to say infected, and this will be infected, and this is not infected and not infected. And what is the indicator here? It's positive, negative, positive, negative. So we have all of the different 4 combinations. Now how is this going to work? Let us go give this vector a name. We'll call that random PM index. It can be any name you want. I'm just going to call it that. I'm going to make it PM index. Okay. Now, over here, we can go equals index of PM random PM index of PM index. So the first occurrence that we see is 605. And then we want to look that up. So we can look up equals lookup this value in here and give me this result. So I got a 605. 605 is bigger than 191, so it gives me not infected. So now let's program the second row. Equals index equals lookup of this cell, comma, in there, comma, and that gives me a negative answer. So with the value of 605, I get not infected, negative. Let's just check a few others here. We'll go to trial information, and we'll look at some different ones. So that's trial 1. If I go to trial 2, still the same. I'm looking for something different here on row 12 and 13. There's one. So 178. 178 is less than 191. So now I'm going to get not infected and positive. Very good. So let's calculate a metric which is equal to this value and this value. May not make a lot of sense, but it says not infected and a positive. Let's define that as an output variable. And we'll call this the result, okay? Now what I want to know is what's the probability of getting infected positive result? I'm going to do that by going over here to SIPmath, chance of whatever. Output is this variable here, and is equal to, down here I'm going to say infected, positive. We'll say OK. It's 8%. I'm going to copy that across, and then I'm simply going to come over here, and I'm going to say negative 2%. And over here, I'm going to put not infected 9%. And over here, I'm going to say not infected and negative. And we can see that these probabilities here correspond to the probabilities here. So then how do we utilize this in our model? Well, we have the result of reality and indicator here for each of our trials. And so what we'll do is we'll use in our model, we'll look at the indicator result. And based on that indicator, have a decision policy. And then we'll see the reality and calculate the results. This methodology for evaluating a conditional probability matrix using Bayes can be applied to multiple matrices. They can even be connected. So consider this for an alternative to a decision tree, particularly when you have a lot of uncertainties that you'd also like to include in the analysis. Hope you found this useful. Thank you for watching.